A little bit. Now, what'd you find?
It didn't do anything.
Okay, yeah, so whenever you multiply a 2 by 2, these are all 2 by 2 matrices, right? So I need to multiply by a 2 by 2 identity matrix. Whenever you multiply a matrix by the identity matrix, it gives you back same thing, yeah. So this is the matrix equivalent of the letter 1, okay, of the identity. It's the equivalent of the identity number for multiplication. Let's everybody put away iPods, all that stuff, put all that stuff away. We got lots to do here. This will be, I think we'll get through stuff today, though. I believe we'll get to a point where tomorrow we can go to the lab and you guys can work on this stuff a little bit, at least for part of the period. Then you get 3 days straight in the lab after that. Okay, so there's one thing we figured out. What about down here? Did anybody get this far down here?
No.
Okay, well, we'll get to that. We'll get to that. Let's scoot on here a little bit. Okay, so yeah, this identity matrix thing. Now let me show you on your calculator where you can find the identity matrix. Okay, if you go to the matrix menu, and you go to matrix screen, go to the math menu, scoot over to the math menu, and notice number 5 there, it says identity, okay? So if I choose 5, it says identity, and then it has an open bracket there, open set of parentheses, so it wants me to tell it something. What do you suppose I need to tell it? Here's an example of a 2 by 2 identity matrix. Here's a 3 by 3 identity matrix. So there's not just one. What do you suppose I probably need to tell it? Which kind? Let's just try. What if I put a 2 in there? What do you think it's going to do? Hey, that. Okay, let's replace that with a 5. I'll go second enter and just go back and overwrite that with 5. See what it does? Okay. So an identity matrix is always square. It has to be, right? But we want to know it's square. How big is square? How many rows by how many columns? So this is a square 5 by 5. So that's kind of nice. You don't have to actually, had you gone through that whole example there at the beginning, you probably would have gotten to a point where you would have, well, you did. You created some identity matrices and probably stored them as D or something, right? You don't have to do that. You can call up an identity matrix of any size you want just from that matrix math menu. You don't have to create it by hand. It'll do it for you. Okay? All right. So, if A is any n by n matrix and I is the n by n identity matrix, then I times A equals A and A times I equals A. So in other words, we can multiply any matrix by the identity matrix from the left or the right, and it still acts like a 1. We got to be careful with that, though. Remember what we talked about yesterday? We said that although when we add matrices, all the normal properties of real numbers apply. We can add them in any order we want to. We can commute them. We can group them. Associative property applies. Distributive property applies. All that stuff. For multiplication, not the case. Remember we said that the order matters. In general, we said yesterday that matrix A times matrix B is not equal to matrix B times matrix A. In fact, usually, if we can multiply those two matrices in one order, we can't in the other order. We might be able to, but we might not also. What if A was a 3 by 4 and B was a 4 by 5? I can multiply them in that order, can't I? Because the 4s match up. But if I commute those matrices, I'll have the 4 by 5 in front, and then the 3 by 4, and the inside numbers won't match up, and so they will not multiply. Okay, so you got to be careful about that. That's the one real pitfall that you got to be careful of when you're doing matrix arithmetic. Two n by n matrices are inverses of each other if their product, either order, you know, it doesn't matter if I switch the order, if I commute them, is always the identity matrix. Now that ought to seem familiar, because think what we did if we go back to our earlier in the year, our talk about properties of real numbers. We said something like this. We said for multiplication, any number, call it A, times the identity number for multiplication, 1, equals A, right? Okay, that's good. Now, that was our identity property for multiplication. Multiply a number times the identity number and you get the number back. Now, that was linked to another property, the inverse property. Remember how that one went? That one said we're going to multiply A times something in such a way that we can get back the identity number 1. And whatever's inside that box, we call the inverse, the multiplicative inverse. What was that for multiplication? What would I multiply a number by to get back 1? What would I multiply 4 by to get the answer 1? 1/4. Yeah. What would I multiply 2/3 by to get 1? 3/2. So what goes in the box is always going to be the reciprocal, right? And we said that the multiplicative inverse is equal to the reciprocal. Okay? Same kind of thing is true for matrices. We get the same relationship going on here. Only it's not a reciprocal. It's a different matrix. It's an inverse matrix. So let's take an example of this. For example, A times B. A and B are inverses of each other. Okay? B is the inverse of A, and A is the inverse of B. If I multiply those two matrices together, and we could demonstrate that on our calculators if we want to, we're going to get back a 2x2 identity matrix. That's proof that these two matrices are inverses of each other. So that's an easy way for us to always check. If we want to check to see if matrices are inverses, we just multiply them and see if we get back the identity matrix. It's not as easy as it is for normal multiplication. It's easy to see if numbers are reciprocals. They're just the flip of each other, right? We can just, by inspection, we can look and tell, but with matrices, we actually have to multiply them together and see if they give us back the identity matrix. And if we commute those, it still works. Okay, how do we do inverses? Let's look at an example here. Well, first let me just show you. This is how you do the inverse of a 2x2 matrix. Take a quick look at this, but it gets a lot harder with bigger matrices, and so we're just going to use our calculators. The inverse, if this is matrix A, okay, if the elements in order are just A, B, C, D, then look what you do to get the inverse of A. First of all, we take the reciprocal of the determinant that we talked about yesterday of the matrix, times, look what we do with these entries. We're going to take the downward sloping diagonal, and we're just going to flip everything along that diagonal. So the A and the D are going to switch places. And then along the upward sloping diagonal, the numbers stay the same, but we just multiply by -1. Why do we do that? Just because it works. And so, you know, if we remember what the determinant looks like. Remember, the determinant is just the downward diagonal minus the product of the downward diagonal minus the upward diagonal. So A times D minus C times B. So there's the reciprocal of the determinant times this new matrix. Okay, but, you know, we're going to do it on our calculator. So how do we do that on our calculator? Let's look at an example. Let's find the inverse of this on our calculator. It's real simple, as you probably expect on the calculator. All we do is input the matrix, so let's do that real quick. Second matrix, edit, enter. So for matrix A, it's a 2x2, right? So 2, enter 2. And then 3, 1, 4, 2. Okay. And now that we've got the matrix in there, we'll just quit. And to do the inverse, we're just going to call up the matrix. So we go to the matrix menu and hit enter to call up matrix A. And then all we do is we hit the button in front of matrix, which is inverse, the inverse button. So if I push the inverse button, I just get that -1 notation. That looks a little strange, but that's what we use. That's the notation that's real consistent for us in math. When we talk about inverse functions, that's how we say them. For example, if we were just in general, and we'll talk more about this later in the year, if f of x is some function, then that's how we denote the inverse function of f of x. It's just that power up there. With trig functions, and we won't do this so much this year, but next year you will, the inverse of a sine function, we can either write like that, and that doesn't mean sine x to the -1 power. It doesn't mean that. It means the inverse sine. Or another way to write that is that way. But this is a real common notation for us. So it might seem strange, but it's not. You'll see it again and again. Now watch what happens if we hit enter. Oops. Just drawing on my calculator. Okay. Yeah, see, it gives us back the inverse matrix. Let's just check and see if that's what they got. Okay, now theirs, it looks like they've got it in fractional form. Do we want ours in fractional form? Oh, maybe. How do we do that? Yeah, I can take this whole matrix. This is pretty cool. Take the whole matrix and go math, convert to fraction. Look what it does. It's the whole matrix in fractional form. Okay. Now, just to verify, if we wanted to, just to demonstrate that if I multiply this by A, what should I get back? Because this is the inverse of A, right? Okay, let's try that. If I go times, so it'll take this answer times matrix A. Yeah, look what I get back. The identity matrix. I knew I had to, though, didn't I? Because that's what happens when I multiply inverse matrices together. Okay? Is it possible that there are some matrices that don't have inverses? Yeah, it is. In fact, what'll tell you whether the matrix has an inverse is whether or not it has a determinant. If there is no determinant that you can calculate from a matrix, then, or if the value of the determinant is 0. See, look, let me go back to this previous page for just a second. Look here, if the inverse of matrix A is the reciprocal of the determinant times this jumbled matrix we're creating, well, what if the value of the determinant was 0? Wouldn't that be a problem? Because we can't divide by 0. That's one of our rules for real numbers. We can't divide by 0, and we can't take a square root of a negative number, right? So in a case where the determinant equaled 0, or for some reason was undefined, then we couldn't even do an inverse, and that occasionally will happen. We'll see it happen. Okay. Applications of this. What's this for? Here's what it's for. Okay? Things like this. What if I want to solve a matrix equation? Let's say I've got matrix A times X, the unknown matrix X, equals matrix B. And I want to solve for X. Now, what would we normally do with that if these were numbers instead of matrices? What if this was just something like AX equals B, numbers instead of matrices? How would we isolate X there? It's pretty simple. We'd divide by A, right? Now, isn't dividing by A, though, and you're exactly correct, that's what we would do. Divide both sides by A. Isn't that equivalent to multiplying by 1 over A? Doesn't that make sense? Okay, so I could rewrite this if I wanted to as 1 over A times A equals 1 over A whoops, times B, right? And 1 over A times A gives us back the identity. Whoops, I get my X in there, don't I? My X. 1 over A times A gives us back, the reciprocal of A times A gives us back the identity number for multiplication, which is 1. Right? Those two, this product right there combines into a 1 times X equals 1 over A times B. And 1 over X is just X, right? Now, we can't divide matrices in the same way that we divide real numbers, but we can do this. We can multiply by the inverse. So if we want to get this X by itself, watch what we can do. Okay, we'll let the calculator find the inverse of A. But then here's our trick. The inverse of A, if I multiply both sides from the left by the inverse of A, what's this part going to give us back? What's the inverse of A times A? Yeah, it's I, right? It's the matrix equivalent of 1. So that's what we're doing. There's A inverse times A times X equals A inverse times B. Well, as you told me, that's going to become I times X, which is just X. Right? The identity matrix times X is just plain old X. And so the answer is just this. A inverse times B. Okay, see how that works? So that's where these inverses are so useful to us. Let's do this one on our calculator, just to show you that this might look complicated, but on the calculator it's pretty darn simple. So if I want to do this problem up here, this is matrix A, that's matrix B, I know that to isolate X, I'm just going to, divide both sides by matrix A, which is the same thing as multiplying by A inverse from the left. So let's input both of these matrices. Okay, so we'll go over and edit matrix A to be this guy. So 4, -1, -3, 1. We'll edit matrix B to be this guy. Okay, now we can quit. So we've entered, this is A and this is B. Now all we have to do, remember, is this. We know that if we multiply both sides from the left by A inverse, that's going to isolate the X. And so the answer is just going to be A inverse times B, right? That's our matrix way of dividing by A, is multiplying by the inverse from the left. So all I've got to do then is call up matrix A, invert it, and then multiply from the left by matrix B. Okay, does that make sense? That's my way of dividing B by A to get X by itself. And if I hit enter, look what I get. Yeah. Okay. Pretty handy. Okay, now why? So that's why we introduce inverses. The main reason for us this year, that's the only reason, is to solve matrix problems. Do matrix algebra. Okay, and here it just mentions that if determinant of A is 0, then it doesn't have an inverse. The inverse of a 3x3 matrix is difficult to compute by hand, and a 4x4 or a 5x5 is really difficult, but calculator does it quickly. Okay, I want to show you a little. I actually put some of these in the assignment. I think this is kind of cool. It's you have to humor me on this a little bit. Cryptography is the science of easily encrypting messages in a way where you can keep them secret, but also decrypt them, decode them easily. I mean, with the advent of computers, it's really easy to do. But this was something that people actually did, not that long ago. This was an easy way to using matrices was an easy way to encrypt messages that was really hard to break. Here's how you can do it. If you assign all of the letters of the alphabet a number, including the space equaling 0, so you can put a space in between words. And you're not going to have any punctuation, but we could add that if we wanted to. If we assign them letters in the way you'd expect, then we can easily encode messages like this. All we have to do, if we want to create the message "get help," we're just going to convert each of these numbers and spaces into letters and spaces into a number. So it's just going to look like that. And we're going to break them into matrices of a certain size. We'll make them small and simple. We'll make them 1x2 matrices. Okay? So each of those, you see how that works, right? And at the end, if it was an odd number at the end, we just would have a space. It just would end up being a 0. Okay? So once we've created this is our uncoded message. Now we've got to encode it. We've got to multiply it by some random matrix to encode it so nobody can read it. So we'll just randomly generate this matrix. How about just some random 2x2 matrix, and we'll remember what that is. We'll write that down somewhere. If we multiply matrix A by each of these row matrices that we created, it's going to look like nonsense, right? So here's the uncoded row matrix. Here's our encoding matrix. If we multiply the two, we get something random. Now that's not going to make any sense when you try to turn that back to letters. It's going to look like garbage. Okay, so we could do that for all of them. Multiply each little bit of our message by this encoding matrix A. And here's what we get. We get the coded message that's these new numbers instead of the ones we originally started with. That's the one we're going to send out to our secret agent who's out doing spy work or something, right? And then he's going to get this message, and how is he going to decode it? Inverse. Yeah. All he's going to do is he's going to reverse that process. Instead of multiplying by A, he's going to divide by A. But remember what that means. Multiplying by the inverse of A is how we divide matrices. So there's the inverse of A, okay? And so we're going to decode a message with that. Here's the message. I guess this is the return message we got from him. So we got to find the inverse, which we can do with our calculators, and there it is. Okay, there's our decoding matrix. Now we'll take each of we'll group up this coded matrix into pieces, 1x2 pieces. So there's the first piece, and then the second piece is going to be those two, right? And each time we'll multiply by the decoding matrix, and it'll undo the code and turn it into numbers that do now correspond to letters. So if we go all the way through this thing, what do we find here? Well, we go all the way through. There's the last one. Now the uncoded row matrices are as follows. If we line them all up, those were the answers we got after we uncoded them. Let's just convert those back to letters. And we get, I don't know, what's this say? Okay, that's pretty good. Okay, I really didn't pick this one, I promise. So it gives you back a message. Okay, so you get the idea. Okay, yes. Why can't you do that on your calculators? The one, oh, you mean the one that was assigned on that?
Yeah, like the cryptology. How do you do that on your calculator?
Let's pull it up. Let's see. Do you remember what problem it was?
It was like the last two problems on 4, 3, and 4, 4.
Okay. 44. Okay. 44 and 40 from 4.4. Oh, okay. So we got to look in the book. What's the book say? This thing isn't working, or I'd take a picture of this, but. Okay, here, take a look. Here's the problem from the book. We'll do, I think I assigned 40 and 44. Let's look at 41. Same stuff. So 41, we want to use the code on page 225 and the matrix to encode the message. Stay there. So we got to convert these. Here's the matrix. So let's just do the first couple of that. How about? So if I convert those into numbers, what has anybody done that? What's S? 19. Okay, so that's 19, and T would be 20 then. Etc. Right? That makes sense? So if we want to encode this then, we're just going to multiply A by these guys, right? Or I think the order we do it is, okay, so we're going to multiply these guys times A. So we're going to do, for example, 19, 20, right? The row matrix with entries 19, 20 times that. Now, honestly, it's probably faster with small matrices like this. It's probably faster to just do these by hand. It really is. Now, remember how we do that. We're going to, if I multiply a 1 by 2 times a 2 by 2, I'm going to get a 1 by 2, aren't I? Now, to get this first entry, the row 1, column 1 entry, I'm just going to superimpose row 1 with column 1. So it's going to be 19 times 1 plus 20 times 1 is 39. Okay, you can use your calculator if you want to. Everybody see how we got that? First times first plus second times second. Row 1, column 1. To get this entry here, which is row 1, column 2, we'll go row 1, column 2. So 19 times 2 is 38, plus 60 is 98. Okay, so there's our first decoded string, right? And then if we want to do the next, let's do one more. Then I pull down 1, 25 times 1, 2, 1, 3. So 1 times 1 is 1, plus 25 is 26. 1 times 2 is 2, plus 2 plus 75 is 77, etc. Okay? So that's what we're doing for problem 40, you're doing something like that. You're encoding a matrix. Now, problem 44, you're decoding a matrix. So on one like this, it's giving you a string of stuff. Here, we'll do 45, how about? Okay, for these, they're telling us that the decoding matrix, we want to use the inverse of D. We'll just do the first 4 letters, how about? So on 45, it starts off with the string. That's the first 4 numbers of the string. Okay? Now, this is the matrix that was used to code or encode the message. So we need to use its inverse to decode it. So what we want to do then is we want to multiply 21 negative 31 times the inverse of D. Okay, well, real quick, what is the inverse of D? Let's just find that real quick. So what is it again? 2, 3, 1, 2 is the inverse. Okay? So if I do that, then I'm going to get back 21, first times first, right? Row 1, column 1. 21 times 2 is 42. Minus 31 is 11. Row 1, column 2, I'm going to get 21 times 3 is 63. Minus 62 is 1. Okay? And then we got 22, negative 26. Times 2 is 44, minus 26 is 18. Is that right? Yeah. 22 times 3 is 66, minus 52, 14. So the first 4 letters would be this. So what is that? What's the 11th letter? K. K. L. R. N. Okay. So it's Karn something. I don't know. It's some Egyptian name, so it's kind of a strange name. Make sense?
Yeah.
All right.